I wanted to talk about a project that I've been working on off and on for about a year. This is a lamp made by Dyson, and last winter I got a little obsessed with it. These are linear rails from open builds, and it's starting to resemble the range of motion that we saw in the original Dyson lamp. You know what it reminds me of is that riddle where there's a fox, a rabbit, and a cabbage. The microcontroller is communicating with the driver perfectly. For about the 20th time, I designed a new carriage. I managed to implement a drag chain-based cable management solution. I made a PCB. My first PCB. Can't believe I have 60 subscribers, that's so cool. This is the DIY Express. The DIY you can build in a weekend and iterate upon forever. Jake totally came through with this beautiful carriage milled from aluminum. I'm calling this experimental component the Super Track. The heat pipe is sucking heat away from the LED so efficiently. I don't know how people make videos so fast. Recently, I changed almost every component on the DIY control board and added a bunch of new ones. This is like one of the best materials I've ever seen, the newly renamed Open Task Light. I can't help but wonder if we can do better. We have to keep in mind that I'm dumb. We're getting dangerously close to finishing the Open Task Light. Hey everyone, and welcome to the final Open Task Light build log. There's a lot to talk about in this one, so let's get right into it. In the last OTL build log, we forked the base design into clamping and freestanding versions, and prior to that, we did a big overhaul of the electronics to include a temperature sensor, ambient light sensor, our flicker-free LED driver, and a bunch of other improvements. I promised then to come back and show you a new and improved control board, and just a few days ago, I finally ordered the new PCB. I can't wait to assemble it and test it out, show it to you, but I have to wait for it to arrive. So in the meantime, let's make some other improvements. First, there's an issue with the clamping base from the last build log. I showed off this really beautiful bronze sleeve bearing that I was hoping to use with the clamping base, and the intent was to pair this with a cheap aluminum spacer for a precise fit, smooth rotation, and minimal wobble. Unfortunately, while the outer diameter of the spacer matches the 10mm inner diameter of the sleeve bearing on paper, in reality, the spacer ends up being closer to 9.94mm, and I think this 0.06mm discrepancy amplified over the height of the lamp is the primary driver of the wobble. My first instinct was to call a local machinist and see if we could get a more precise 9.99mm spacer made, but that's expensive and I want to avoid adding another custom part to the Open Task Light parts list. What I'd really prefer is an off-the-shelf part that's both cheap and precise. And I think with these three constraints in mind, the simple ball bearing is really hard to beat. It's kind of a strange choice because I'm not interested at all in the spinny bearing part of the bearing. They just happen to be a mass manufactured part that's relatively precise, at least enough for our application. And using a couple of these 10x4mm bearings, we get a consistent outer diameter with a high degree of precision while keeping costs low and sticking to off-the-shelf parts. A stack of 4 of these bearings fits perfectly into the base and reduces wobble significantly, so that's great. It's a bit awkward though because now we have ball bearings nested within a sleeve bearing and the whole thing is just a little redundant. Also, these bronze sleeve bearings are $8 each, so as much as it hurts me to see one of my favorite parts of the lamp go away, I can't help but wonder if there's a good solution out there that doesn't use the sleeve bearing at all. A big constraint of the original solution, the one where the spacer acted as both a support and a crude bearing, was I had to be really careful to avoid clamping down too tightly on the aluminum spacer because while a tighter fit reduced wobble, a fit that was too tight prevented the lamp from rotating smoothly at all. These bearings actually eliminate that problem and I can clamp down on them as hard as I want and know that they'll always spin freely. So I modified the base design with a clamping feature for a really tight grip. I'm using an embedded square nut, a vertical slit in the base, and a 20mm screw to pull the perimeter tightly around the bearings. I've prototyped this with both an M3 screw and the familiar low-profile M5 screws found all over the lamp, and I'm not really sure which one I prefer yet, so I'm going to keep them on my desk and tinker with them a little while longer until I decide which one I like more. Which one do you prefer? To be honest though, I'm a little heartbroken at the loss of the bronze sleeve bearing. I just really liked the way that it looked. But I also really like the idea that people will have the option to upgrade to whatever solution feels right to them, whether that's the clamping base or the bronze sleeve bearing. So I'll definitely be releasing all the 3D files for all of these solutions so that people can choose for themselves. With the lamp less wobbly than ever, it's time to work on an issue that's been bothering me for quite a while. The material I've been prototyping with, this matte black PLA, is, in my opinion, one of the best looking filaments out there. And in almost every case, this PLA is a great material choice for the open task light, except for one place, the carriage. There's a lot of stresses applied to the carriage, not just from moving the lamp with these giant levers, but also through pressure from the wheels via the tightened eccentric spacers. Over time, these forces have warped the carriage and misaligned it to the point that it's starting to affect the lamp's function a little bit. I know from using the aluminum carriage just how good the lamp can feel with a really stiff carriage, and that has me wanting to explore some alternative carriage materials. What I'm hoping to do here is find this sweet spot of cost, stiffness, and printability. So to answer that question, I want to do a little test to find the perfect materials sweet spot. And I think I've got a good range of materials to test with, starting with the matte PLA as a baseline. I've also got some matte PETG, carbon reinforced PET, a nylon blend, and a polycarbonate carbon fiber blend. I chose these filaments in particular for their promise of increased strength, but also because these specific formulations are evidently easier to print with reduced warping and improved bed adhesion compared to similar formulations. What we want to test is rigidity, the ability for the printed part to hold its shape. And to test this, I made a test piece that roughly resembles the carriage geometry, and I've printed them all with print settings and orientation similar to what I'd use for the carriage. 5 perimeters, 35% 3D honeycomb infill, and 6 bottom and top layers. Before we get into the test, this is my first time working with a lot of these filaments, and I already have some thoughts just from handling them for a little bit. First, they were all very easy to print on the Prusa Mark IV's using a 0.4mm obsidian nozzle with no enclosure and no specialty add-ons needed. I already have a real soft spot for one of these in particular, and that's the polycarbonate carbon fiber blend, which even though it looks just like a normal 3D printed part, it feels really premium. It has this really nice texture and sounds kind of like glassy. I'll try to add in some audio of what it sounds like to handle this thing, but I have a real bias for this, so I'm kind of rooting for it and hoping it wins, but I'll let the data determine that. Before going into the official test, I wanted to do like a little fun prediction just from handling these and seeing how they flex. So if I had to rank them from most stiff to least stiff, I'd probably go with polycarbonate carbon fiber blend first, though my judgment is very clouded with this because I just like the material so much, so keep that in mind. Followed by the PET carbon fiber blend. And then from there, I actually think that the PLA is going to do pretty well, maybe somewhere in the middle. So I'm going to put that right in the middle. And then the last two, I think just from feeling them, I could totally be wrong. I think the PETG is going to be next. And then lastly, I actually think the nylon feels the least stiff to me. It tends to flex. And while I think nylon has a proven record of being really tough and resilient, I don't know if it's going to be the stiffest. So I actually expect that to finish last. This is all obviously based on rough feel. So let's see how my ranking holds up against some actual data. I'll clamp one end of the piece to the desk and hang a weight from the other end and use this bracket from my monitor stand project to measure how far the part flexes under load. In theory, the one with the smallest deflection is the most rigid and a candidate for the best material for the carriage. I was thinking using digital calipers would be like a really dead simple, high resolution way to measure deflection across the test pieces, but I quickly realized how much room for error this method has. Even though I have a common point of reference in this steel plate, the measurement spot can move around quite a bit, and the calipers have this tendency to actually alter the results whenever they touch the test piece. Rather than making a jig to fix the calipers in place, I opted to just measure the results optically using a camera on a tripod, and with some calibration I can translate the deflection from the image into actual deflection in millimeters and get a really accurate sense of how the material is performing. And the setup worked really well. I was able to use the calipers and the image to calculate the deflection for each material in actual millimeters. So that's what you're seeing in this graph. PLA is coming in last. It deflected a whole 28 millimeters, followed closely by PETG at 21 millimeters. Nylon came in third at 16.82, and then there's two kind of standouts here towards the right with PETCF coming in at 8.15 millimeters, and then polycarbonate carbon fiber blend coming in at 8.85. So not too surprising, and a little bit off from what I estimated, but it basically follows the trend of like more exotic and more expensive from left to right. But I wanted to know exactly like how much performance I'm getting per dollar. So I made another graph which which is measuring the cost per test piece for each material. So PLA is obviously very cheap. It's only 50 cents per part. That's what we love about PLA. The PETG is, in this case, significantly more expensive than the PLA. That's because I'm using the Prusament matte black PETG, which is a little bit more expensive. And then we have these three on the right, which are like the more exotic ones. So nylon, PET, CF, and PCCF are all above $1.50 per part, 170, 194, 198. So while I'm not all too concerned with price when all the parts are below $2, I do kind of want to find that center of the Venn diagram where we have really good stiffness performance, pretty low cost, and good printability. So this is just a comparison of cost versus deflection. So ideally, both of these would be very low. So we'd have low cost and low deflection, and it'd be somewhere in this area, which you can see is kind of a ghost town right now, but I guess that's kind of understandable. Like you have to pay for that stiffness. So PLA is super cheap and it bends a lot. And our PETCF, PCCF, and nylon are all over here on the right, around the $2 mark, but super stiff. The nylon didn't perform very well, and unfortunately I found out during the test, like deep within the data sheet on this, that it prefers to be annealed post-printing. So I did end up annealing this part and it still didn't perform very well and it shrunk. So if I had to do this over again, I would not even test this part because it's disqualified for being too fussy, and I would have tested something else. The real standout here for me is the PET-CF because it really hits like right in the middle of that Venn diagram. Not only is it the best performer in terms of stiffness, the part cost is about $170. And for me, most importantly, it is as easy to print, in my experience, as the PETG, whereas the nylon and the PCCF were a bit fussy to print. So yeah, I'm really happy to find the sweet spot right here, the PETCF. It's nice to have a standout that kind of just makes sense in all the different characteristics. I already printed a carriage with this just to feel it, and it feels really good. Like the stiffness adds this level of like precision and responsiveness when moving the lamp around. So while it's never going to be as good as the aluminum carriage, it's a really good alternative at $1.70 for the part. Since this prints a lot like PETG, it prints really well on the satin PEI sheets, and so the print surface has this really nice finish, and it looks even better than the old carriage while blending in with all the other black parts on the OpenTask Lite. So I'm going to go forward with the PET carbon fiber blend. There's a bunch of PLA variants that I'd really like to test, like there's like PLA Plus and Tough PLA and stuff like that, which all could be contenders for like occupying this space on the graph right here where it'd be very cheap and very stiff, but I'm over budget. So if there's like a champion material that you have in mind that you're wondering why I didn't test, that's probably why I can't spend any more money on this. A big part of this project for me has been accepting that parts are not ever going to be perfect, and really it's always like this shifting Venn diagram of characteristics. And I think with this experiment, we've struck a really good balance of stiffness, affordability, and ease of printing. So I'm really happy with this, and it's time to move on. Or maybe that's just what I'm telling myself because the updated control board PCB finally arrived and I really want to get it assembled and in the lamp. But before I do that, I need to prepare the horizontal rail with a couple of cool upgrades. One downside of taking 4 years to finish your projects is that sometimes your parts get discontinued. That's what happened with this LED. It's no longer available, which is a problem considering this is supposed to be a lamp. Luckily, the replacement I found isn't just a replacement. At 95 CRI, it's a 2 CRI upgrade over the old LED and a full 5 CRI better than the Dyson Solar Cycle. Throughout this project, and especially now towards the end, I am always trying to find ways to minimize fuss and make the assembly process easier and more precise. I found this LED holder, which is functionally identical to the current one, but has these push-in wire terminals for solderless assembly, which eliminates a small but messy step from the assembly process and allows for easy swapping of the LED chip in the future. Just above the LED holder is the heat pipe, the cooling solution that makes using a high-power LED like this possible. It fits perfectly in the channel of the aluminum rail, but I only ever utilize about half the length of this channel. For the last upgrade, I'm stepping up from a 300 to a 400 millimeter heat pipe to pull heat even farther away from the LED and hopefully improve cooling performance. With some thermal epoxy to secure the heat pipe in place, and of course some custom clamps to help me out, I can secure the new heat pipe in the channel and assemble the rest of the LED assembly. So this new assembly is definitely looking a lot cleaner, and I think it's mostly due to this new LED holder. For some reason, the old one is just full of all these gaps and holes, and this new one not only upgrades the wiring, but closes up a lot of those holes, which makes it look a lot tidier and also should help reduce light leak in the fully assembled lamp. This idea of fussiness has come up a lot during this build log, and it definitely came to mind as I was assembling this, gluing the heat pipe in place and clamping it in and trying to align everything just so it crosses my mind, like, can I do this 50 to 100 times to a high degree of accuracy? And for this assembly, I think the answer is, yeah, I probably could do it that many times, but I want to optimize some stuff. I'm definitely going to use a lower viscosity thermal epoxy for the channel, and I'll use something that is a little bit easier to deposit within the rail. And while these custom clamps definitely did help a lot to secure the heat pipe in place, I need to come up with something a bit faster and better for like batch making these. But other than the process stuff, I think this assembly was a success, and we are fully prepared to move on to the control board. Taking the time for little upgrades like this really make the lamp better in the long run, and you can do the same for your brain with today's sponsor, Brilliant. Brilliant helps you upgrade your brain to become a better problem solver with thousands of courses in math, science, programming, data analysis, and AI. I don't know about you, but it's really easy for me to feel overwhelmed in the face of new, challenging things. Whether it's learning a new topic like electronics or learning a new language, the sheer scale of what I need to know is really intimidating. One thing I really like about Brilliant is it takes these complex topics and breaks them down into smaller pieces so you can just approach these new topics one day at a time. Brilliant even has a course in circuits which introduces you to the foundational principles like current, voltage, and resistance needed to design and troubleshoot electronics in your own projects. To learn for free on Brilliant, visit brilliant.org/Stephen Bennett, or scan the QR code on screen, or visit the link in the description. Brilliant's also going to give you 20% off their annual premium subscription, which gives you daily access to everything on Brilliant. Thank you, Brilliant. It took a few months and a lot of learning to finally pull the trigger and order this thing, but version 2 of the control board PCB is finally here. I originally set out to make this board hand solderable, as in using only a soldering iron, and while that's still technically possible, it would be pretty rough. I'm hoping to make a bunch of these boards for future OpenTask Lite makers, so I need a process that's fast and repeatable with a high success rate. So for that reason, I chose relatively large SMD components wherever I could, but I'm using stencils to quickly and precisely apply solder paste, then placing the components by hand. Starting with the ambient light sensor and capacitor on the bottom of the board, I'm using a small hot plate to melt the solder paste and secure the parts in place. From here, I flip the board over and put it back in my stencil jig and repeat to add the bulk of the secondary components like the IC switch, the temperature sensor, and various resistors, capacitors, and diodes on the other side of the board. And this whole process went shockingly well for my first try. The components are super tidy and the connections seem just about perfect, the only exception being these large capacitors. I had to come back in and solder these again by hand for a good connection, so in the future I'll just do these with a soldering iron. The through-hole components like the capacitive pins, QT Py, buck converter, and LED driver come last, and these get their legs trimmed before being hand soldered, leaving a pretty clean and pretty flush surface on the underside. Soldering these through-hole components upside down like this was a bit tricky, so I think it's another prime opportunity for a future 3D printed jig. Seems like I'm going to be making a lot of those coming up. But for now, I only need one, and I have to say I'm really happy with how this turned out. Outside of the increased length and the new mounting system and obviously the less ostentatious branding, here are a couple of highlights of the new board. First, I flipped the QT Py 180 degrees, and the reason I did this is so that when it's mounted in the housing, so when it's fixed in here, before I had an access hole cut out so that you could plug in a USB cable and reprogram it, but I don't actually really like the look of the access hole. If you flip this around, you can actually fit a USB cable into the channel of the aluminum rail that goes here. And just have that feed out the back. So I'll show you that once it's all assembled. The new arrangement also gives you access to this Stemma QD port, and this is kind of cool because if you're tinkering with the OpenTaskLite and you want to add something new, whether it's something simple like a color temperature sensor or something complex like an OLED screen, it wouldn't require a new board or any new wiring or anything, just this Stemma QT connector, and you have easy access now to that. In previous build logs, I talked about this problem that I had with competing power sources on the QT Py, where if you had external power and USB power plugged in at the same time, I had this fear that it would fry the board, and I had a couple of fried boards where I thought this was the culprit. The obstacle here is you really need a reliable way to detect when there's a USB cable plugged in, and there's just not a good way to do that. There is a 5-volt pin on the QT Py, but that's the same pin we use for external power. So with either power source, that pin is always going to be 5 volts, so you can't really look at it for any meaningful data. And because of that limitation, I just couldn't find a reliable way to distinguish between the two possible power sources. But while puzzling over this and tried to figure it out, I basically torture tested this QT Py with competing power sources and hot swapping power and plugging in and unplugging USB cables, and the QT Py didn't mind at all. It seems basically like more than happy to just stay powered up regardless of the power source. Now there's a diode on the board which prevents backfeeding from the QT Py into the buck converter, and there's an onboard diode on the QT Py that prevents backfeeding to the host, so you're not going to fry your computer if you plug in this QT Py. My theory now is that there's a better explanation for those fried boards I had in the past, and I have a couple of possibilities in mind for what was doing that. But this problem just isn't present anymore. I can't replicate it. So I hope this doesn't come back to bite me, but it's not a problem right now. So I'm simplifying the board and removing all the attempts at power selection logic, which weren't even working anyway. A couple of other improvements include the addition of a ground plane on this board. It's not something I had or knew how to do with the first board, and it was necessary because the routing of the traces got a bit more complicated with all these new components. So it helped me out quite a bit, and from what I hear, it's kind of best practice anyway. And I also took the opportunity to go in and beef up some of these traces, especially like the 24-volt line that's going to the LED driver. That's much thicker now than it was on the previous board where they were all quite tiny. I need to give a big thank you to Josh for doing a design review of this PCB with me before I ordered it, and he helped me clean up the schematic quite a bit, and I learned a lot from that. So thank you, Josh, and thank you to everyone else who helped me with this new board. I was working way outside of my comfort zone, so I really appreciate your help. Though I guess I should be a little bit careful with my thanks before I even test out this board. I don't know if it works yet. I still need to plug it in. And I remember this moment on the first board where I really didn't think it would work before I plugged it in, and I was really nervous. And I think I'm even more nervous with this board because it's just so much more complex. If something doesn't work, it's going to take quite a lot of tinkering to figure out what the problem is. So I'm very nervous to plug this in. I messed up. I went to plug in the QT Py to add the libraries and install CircuitPython and upload the code, and it didn't boot up. It's not booting up. And I didn't test. I should have prepped the QT Py and tested it before I put it on the board, but I didn't. I just took it out of the packaging and then put it right on the board because I was so excited about it. These breakout boards, these little dev boards, in my experience, it's really hard to remove them once they're installed on a PCB because of just there's 14 headers that all need to be removed at the same time. So I tried using my little plunger to suck up some of the solder, but I can't get it out of the little crevices. So I think I have to, I'm going to try to take it out. I'm going to try a little bit longer to take it out, but if I can't get it out, I'm going to have to remake the board already. Which is annoying. I should have tested this out. I should have tested the QT Py and prepped it before I even installed it. I should have gone in with a known working QT Py. So I'm annoyed with myself. I don't have multiples of a lot of these components. I just ordered enough to make the one board to test it out to see if the components would even work or if I needed to change any of them. So I'll probably have to like deconstruct most of this, so that'll take a while, or I'd have to order new ones, and it's Friday, so they wouldn't come until Monday at the earliest. I have a hot plate. So put I might put it on there. I might put this on the hot plate and just melt everything and see if I can pull the components off. So I just used the hot plate to desolder a bunch of these components. So I was able to salvage a bunch of those. Everything except for basically the LED driver and the cutie pie I was able to salvage. So the two most expensive components are stuck on the board, but these two that are stuck on the board I can salvage from my breadboard. I would prefer not to take anything out of there just because it's useful for testing and stuff, but I'll take those temporarily and I'll refill them later on. So I think I have enough here to make another version of the control board real quick. All right, I just assembled a new board. It wasn't that bad. All the components are on here, but when I plug in the cutie pie to USB, and this is a known working cutie pie, I get nothing. And I don't know why. Yeah, I wonder if on the old board, so now none of the components are on here. If I plug this in, does it work? Whoa. That's weird. Can you see that? Yeah, you can see the LED. So I removed all the components, all the SMB components from this, and a couple of the through-hole components, and now the cutie pie boots up. So it must be, I have no idea what's going on. One thing I can do is just remove components one by one until it works, and then go from there. I might have to do that. Hello. It's been a couple of hours. I'm holding the camera, which means things are going bad. I figured out the problem. It was the ambient light sensor. So it was soldered on backwards. I flipped it. And the reason for that, I'll show you the footprint and tell me if you think this footprint is misleading. But I put the light sensor like in the inside the perimeter of the footprint, thinking that was the right way. It wasn't. So I fixed that. Now on this second board, the cutie pie was getting power, but it was stuck in this boot loop. It just booted up, got an error, and then rebooted. I tried flashing it. I tried factory resetting it, and it didn't fix it. It just kept looping. So I had a working board with a cutie pie that had power but wasn't booting. Meanwhile, now I knew that the original cutie pie on the original board worked fine, just didn't work when the light sensor was plugged in. So I moved everything back to that first board so that I'd have a working cutie pie, and that's what this is. I wasn't able to move everything just because I'm like soldering things by hand. One of the pads got ripped up on the IC switch, so I didn't get to put that back on, but it should still work. So anyway, I'm gonna try this board with the LED. I already tested the cutie pie, and it sees the temperature sensor. It boots up fine, doesn't complain about anything. I just need to test the LED, and I'm really nervous because I'm really tired and I just want it to work. What should happen is when I turn on the power supply, it should flash, turn off, and then I should be able to turn it back on. I think I have everything. All right, here we go. Yeah, didn't turn on. Yeah, so I'm about to take a break from this. I can't figure out, I don't know what's going on. I don't know what's wrong. I suspect that the absence of the switch, the IC switch, because it's connected to the brightness control pin, that might be throwing it off, but the pad is damaged. The most important pad of the switch is damaged, so I'd have to wire it in a creative way. So, but yeah, for now I have to take a break because I can't work on this anymore today. All right, I'll come back with an update. Hello, good morning. I took a little bit of a break and I took a bit of a sleep and feeling more patient today. So I've just spent some time with the multimeter trying to diagnose this problem of the LED not turning on and really just trying to narrow it down to one particular thing so I can actually address it. And so I started by measuring the output of the QT Py and the input of the LED driver. I monitored those pins to see if the voltage fluctuated as I changed the brightness levels, and it did. Then I went on to the LED output to see, is the expected high voltage output going to the LED? And it was. I also tested what should be the same voltage level on the cable header, and that was fine too. So that brought me to the LED, which is really the only place where there are variables left, because everything up until that point is working fine. It's just when it gets to the LED, it's not working correctly. I looked a little bit closer and I noticed that I had flipped the leads, the positive and negative leads on the LED. I just miscalculated which one was positive and negative, even though I have it marked on my PCB. And based on that troubleshooting, it might just be that simple. I don't have to take anything apart. I just have to flip the leads. So let's find out. So that was quite the adventure getting the new control board to work, and in light of recent events, I've decided to change the way I mount the QT Py to the control board. Rather than soldering it directly to the board, I'm using these little headers so that it's easily removable and easily replaceable, potentially easily upgradable. And looking back, I'm actually glad that I ran into these issues because this is such a solid upgrade to make, and it took very little effort to implement, and I think it might get some people out of some jams. If you remember before, I was showing off that QT Py connector, and I've actually been playing around with it a little bit with this OLED screen, and it's really fun, and I think there's more potential here than I realized at first. So I'm really excited to see what people do with this on their own builds. And finally, eagle-eyed viewers will notice that you can see the lens sticking out from the enclosure here, and the reason for that is I redesigned the heat pipe bracket recently to lower the LED a little bit, just to give the electronics and the heat pipe a little bit of extra room, and that obviously lowered the lens a bit, and now it's sticking out. So I know it doesn't look very good right now, but I'm on it, so no worries. How about another experiment? So with the new control board working, I can do a test that I've been wanting to do for a while, which is with everything assembled, with it all sealed up and tidy, with the 400 millimeter heat pipe, what max temperature can I reach inside the LED housing? The reason I want to know that is because I'm currently using PLA for the electronics housing, and the glass transition temperature of PLA is about 50 something degrees Celsius, maybe right around 50 if I remember right. And I want to know if my PLA can withstand the temperature that the housing is going to reach. So if you remember a few build logs ago, I did a test of the heat pipe where I hooked up a bunch of temperature sensors along the lamp, and I measured the performance of the heat pipe compared to the heat bracket. And I've replicated that here again, except much simpler. I'm only measuring the housing temperature because right now that's all I care about. And other than that, I'm doing the test exactly like I did before. So I'm running it at max brightness for 1 hour and taking a photo of the thermometer every 30 seconds. And after it finishes, I can do a little breakdown of the temperature over time and see where the max temperature is. So hopefully we never hit that temperature threshold, but we'll have to wait for the data and see. Right now, I'm 13 minutes in and the housing temperature is 35.7 degrees Celsius and the room temperature is about 25 degrees Celsius. So yeah, we'll see where we end up. All right, so I just finished up the test and the results are really, really good. A couple things to note before we get into the results. I wanted to make this like a true torture test, so that's why you see the LED or the lamp head so close to the desk. I want it to be like worst case scenario, and in this position, all the light from the LED creates this like literal hotspot where the temperature is very high, and a lot of that is reflected back up into the enclosure, so that's like the worst case scenario. This hotspot is actually really hot. I measured it during the test, and this area on the desk is actually hotter than the inside of the housing. So it's a pretty good torture test. While I was waiting for the test to finish, I looked up the actual glass transition temperature of this PLA, and I was way off. It's not 50 degrees, it's 60 degrees. And I didn't clarify before, the glass transition temperature is the temperature at which the material softens. So it's not melting, but it could potentially deform, or it's more prone to deforming. The melt temperature, which is when it becomes liquid, for this material is actually 160. So it's like 2.5 times the glass transition temperature, but deformation would still be really bad for these parts. So we want to make sure it's not getting so warm that it easily deforms, and that's why it's my ballpark. This one's embarrassing, but 45 minutes into the test, I remembered that there's a temperature sensor on the control board that is more accurate and higher resolution than this external one that I've been using, but whatever. I checked in on the built-in sensor during the test, and it was in agreement with this external thermometer, so I guess it doubled as a verification of the internal temperature sensor, but that was kind of silly. In this case, either sensor is just fine, so let's jump into the data. So there's not that much here except just good results. On this graph, the top of the vertical axis is the glass transition temperature, so 60 degrees, and we're trying to stay as far below that as we possibly can, and looking at the data, we're way below that. The average housing temperature doesn't really matter. This is actually the maximum. So the max housing temperature is the one that we want, and we never surpassed 39.5 degrees. If you look at the internal sensor, it would say 39.875 was the maximum, but still under 40, which means we're 20 degrees away from the glass transition temperature. And once it hits about like 39.5 degrees or so, it really flattens out. So the data looks really good. In reality, just touching the housing, it wasn't warm to the touch at all. All the heat was going into the heat pipe and into the horizontal rail. So that was great. I was actually going into this test thinking I was justifying a change away from PLA to something like PETG just because of temperature concerns and deformation of the parts. But looking at this, we're not even close to the glass transition temperature, so I can't really see a reason to justify a material change when this material is working so well. This is a great outcome because I love this material, and despite what you might think based on the carriage test, I don't want to use exotic materials unless I absolutely have to. So for the housing at least, we're safe with good old-fashioned PLA. And with that, the OpenTask Lite has taken a huge step towards being finished. The control board is in place and working and smarter than ever. The cooling system is running the LED cool and efficiently, and the clamping base is super sturdy while embodying a lot of the project goals. It's taken a while to get here to the last build log, and I hope you're here because you've enjoyed going through this process with me. At the beginning, I really didn't think that I would be able to do this. I remember the first problem that I had to solve was I had this LED, which has a forward voltage of 34 volts. And I remember thinking, man, how do you even get volts to go that high? And a lot of the problems on this lamp have been like that, where it's just this one little simple thing that I don't know how to do, and I'm just solving one problem at a time over and over. How do I turn the LED on? How do I make the wheels adjustable? How do I change the brightness? How do I connect the LED and the heat pipe? I'm pretty torn right now because as much as I want to finish this and get it in your hands, answering these questions has been so engaging and so rewarding that this has turned into my favorite project ever, and I don't want it to end. I wanted to say for my fellow creative types who are working on their own projects that the build logs are just a slice of my overall process, and they're a very, very refined slice. I don't want the oversimplified problem solution structure of the build logs to suggest that my process is straightforward or carefree, because it isn't, and a lot of us are just taking things one step at a time. Project videos on YouTube just don't really capture this. And so if you are working on your own projects and experiencing lack of motivation or abundance of self-doubt, know that behind the camera, there are people who are working through that same stuff. Back to the OpenTask Lite, there is still one problem I need to solve, and that is the power transfer from one rail through the carriage to the other, and it's a pretty big problem. I do have one more video plan, which is going to be an overview of the final OpenTask Lite, and I wanted to leave at least one last surprise for you in that video, so I'll answer the questions about power delivery there. I am hoping to put together some kits so you can build your own OpenTask Lite, but I'm still working out the details, so I'll cover that in the next video too. Thank you to my incredible patrons and supporters for helping me work on projects like this and share them with you all. Thank you so much. And if you're thinking to yourself, hey, these are projects that I like and I want them to keep going, Patreon is the way to make sure that happens. Big thanks to my Discord mods and community pillars, Joseph and Lucas, for keeping the server running smoothly. And I want to give a shout out to Neil Kefri8179 for being there early on and leaving comments on my very early build logs. I always looked for your comments at those early stages, and it was really motivating to see your positive feedback. So I don't know if you're still watching, but thank you. All right, that's probably enough outro. So thank you for doing this weird project with me. It's been a lot of fun, and I will see you in the next video. See ya.